received his PhD in computer engineering at Politecnico di Milano, Italy in 1989. He is full professor in computer engineering at the University of Milan, Italy since 2000. He has been associate professor at Politecnico di Milano, Italy, and visiting the University of Texas at Austin and at George Mason University. His main research interests are artificial intelligence, computational intelligence, intelligent systems, machine learning, pattern analysis and recognition, signal and image processing, biometrics, intelligent measurement systems, industrial applications, digital processing architectures, fault tolerance, dependability, and cloud computing infrastructures. He has published more than 400 papers in international journals, proceedings of international conferences, books, and book chapters. He is a fellow of IEEE, a distinguished scientist of ACM and senior member of INNS. He has been the IEEE Vice President for Technical Activities. He has been the IEEE Vice President for Technical Activities in 2015, IEEE Director, President of the IEEE Computational Intelligence Society, Vice President for Education of the IEEE Biometrics Council, Vice President for Publications of the IEEE Instrumentation and Measurement Society and the IEEE Systems Council, and Vice President for Membership of the IEEE Computational Intelligence Society. He is Editor-in-Chief of the IEEE Systems Journal from 2013 to 2019, an Associate Editor of the IEEE Transactions on Cloud Computing and IEEE Access, and has been the Associate Editor of IEEE Transactions on Computers, the IEEE Transactions on Neural Networks, and the IEEE Transactions on Instrumentation and Measurement. He received the IEEE Instrumentation and Measurement Society Technical Award in 2002. He is also the Honorary Professor at different universities, including Obuda University, Hungary, Guangdong University of Petrochemical Technology, China, Northeastern University, China, Muroran Institute of Technology, Japan, and the Amity University, India. So I would request Dr. Puri to come on board and present his keynote speech. Over to you, sir.
Thank you for the nice introduction. Ladies and gentlemen, good afternoon. It is really a great pleasure and an honor for me to be here with you today and share with you some ideas about the use of artificial intelligence in advanced Internet of Things architectures in order to support the development of a broad variety of applications in the area of industrial manufacturing, in healthcare, in smart cities, power and energy management, traffic management, really in a broad variety of applications. In particular, we are going to have a quick look to the structure of this architecture, and then we will see how we can improve the functionalities and of the applications and the management of these applications and these infrastructures by using artificial intelligence. As you know, Internet of Things is an architecture which is based on internet, which allow to connect the various devices at the peripheral, sensors, actuators, various type of devices for communication in a very flexible way, so that on the basis of this general internet with these devices connected, we can build the specific infrastructure used for one of the application areas that we are interested in. Basically, what the internet architecture allow us is to connect the specific devices we are interested in to the processing and storage entities and to the user interface for the specific application. As a consequence, Internet of Things is a very distributed model, is a very distributed architecture for collecting data, for processing data, for storing data by reaching out to the environment to which we want to be connected. Is very flexible, since being based on internet allow to adjust the connectivity according to the specific needs of the application, and allow to use heterogeneous components, since the Internet of Things provide some standard interfaces, some standard protocols which allow to use various type of devices by different producers, by using different technologies in a structured way. And is important as infrastructure, since it is very flexible, can be expanded in a modular way, so that we can actually adjust the infrastructure itself to the specific needs of the envisioned applications. And is naturally supporting the data analytic processes based on the data coming directly from the field. But the structure of the Internet of Things embeds also processing and storage components in general, which can be used for dedicated applications. If we want to expand the capabilities in a more flexible way for processing and storage, typically what we are doing nowadays is to add a cloud computing component to the basic Internet of Things infrastructure, so that we can exploit the capabilities, the functionality, the offer of the cloud computing model by using both the infrastructure for storage, connection, and processing, as well as the various applications which are made available in this platform. Cloud computing is useful since it is allow for having a scalable storage and computing support according to the specific needs of the envisioned application, and allow to move the management of the infrastructure from the specific owner of the application to a team of experts which who are available every day, 24 hours per day. Since when we have a really big infrastructure that is serving many users, well, we can afford to pay the technical support for all days of the week, every hour in the day. Since this cost is actually repaid by the availability of the system, the dependability of the system, by the continuity of service for the customers. And since we have many customers, actually, the cost of the technical support can be easily distributed all over these customers, making this cost very affordable, but very rewarding from the point of view of the users. And the cloud infrastructure is composed by a set of sites in which we have hosts connected by subnetworks. We may have also groups of clouds called multi-cloud, provided by different providers. Some are general purpose networks, other are more specialized clouds. And what we can do is to build our application also in the Internet of Things model by picking from a single cloud provider or a multiple set of cloud providers the functionalities that are more appropriate for our specific Internet of Things application. To facilitate the choice, to support the choice in a more dynamic way by considering the specific possibly changing offer of the providers, more and more the concept of cloud federation is growing in the research and in the market, so that we can have a central broker which is distributing the request for the various resources, picking the most appropriate with the most appropriate cost for each specific request, coming from an application that has been deployed in an Internet of Things infrastructure with the connection to a cloud federation eventually, for storage and processing. So basically, in the modern view of the Internet of Things infrastructure, we have the use of the Internet with the devices for input-output connected to the system of the Internet architecture, Internet of Things architecture. But then we have the opportunity of having some local processing with the fog model, for the fog computing model, or if we can stay in the cloud more globally, so that we have much more flexibility in selecting the services, the applications, the amount of storage and processing, which is specific needed for our application. The connection to the system, the infrastructure connecting the various devices in Internet for our specific application needed to show significant capability of dependability and resilience, since we do want to ensure the continuity of service. So we needed to have multiple devices connecting the application to the external world, so that we have a sufficient redundancy to ensure the correctness of the data, even in the presence of possible malfunctioning, defects, faults, and as a consequence, the continuity of service. But we needed to ensure also in our Internet of Things infrastructure the dependability from the point of view of robustness for security. We needed to provide the appropriate support in the infrastructure in order to detect and manage possible attacks, possible threats that we may have to the security. We needed to prevent the intrusion in order to make sure that the behavior of our application is exactly as we designed and not affected by the possible intrusion in the data, in the processing, in denial of service, in various modes, which will prevent our application to run regularly. But we need also to take into account that we need to ensure the data privacy. We, in our application, we may have some information, some data, which need to be protected by privacy according to the specific application. Think about, for example, medical applications in which we do not want that the data of a patient are publicly disclosed, or in the case of industrial Internet of Things, we may not want that the detail of the manufacturing process is observed by someone else, so that the core information, the most relevant information about the manufacturing process are stolen by possible competitors, or the process is damaged by the intrusion in the data. So basically, in order to support the Internet of Things infrastructure, there are really many companies which are investing in artificial intelligence for these applications, and specifically in the sub-symbolic artificial intelligence, also known as computational intelligence, providing environment, tools, components, which are easily usable in applications. There are opportunities for using intelligence tools, components, software which can be directly used by the users who like to understand, extract knowledge from the data, analyze the data, and use this component in their own applications. There are also other more structured offers provided by many companies, small and big companies, to collect the data from the lower level, to collect the data from the sensors, to analyze this data at the very low level, to prepare, enrich the data, extract some relevant characteristics which are strictly related to the application, and provide a better understanding about how the application is working. We can use also components of artificial intelligence as a service, just as a software, a packet, an application closed in itself, which can be connected to other modules of our own applications in a seamless way, so that we do not need to enter in the details of how the artificial intelligence components are structured, how the machine learning techniques are working, but we use the results of these technologies, provided that we have tailored some parameters to our specific application. And in some cases, this tailoring is also supported by tools provided, offered directly by the providers. And this offer can be in general purpose areas, or can be specific in niches of application areas. Then in the market, we have also many other tools which we can use based on artificial intelligence to build our own applications. For example, we may have intelligent interfaces, graphic interfaces. We may have messaging systems. We may have the ability of interacting with agents, artificial intelligence-based agents through speech. We can use vision. We can build an interaction with the system based on the more natural approaches that we as humans are using among us. And then we can have higher level components and tools, for example, user cases that we can replicate in our own specific environment, or we can have tools, systems, applications that we can deploy to run our own specific case. Then we have in the market more general tools which allow to structure data mining, so that when we collect a huge amount of data in our Internet of Things architecture for our specific application, we store them, and we can arrange the analysis to extract relevant data, which give us a better understanding of what is happening in the application. And we have also tools, infrastructures, which allow to extract the knowledge which is embedded in the data, typically by using ontology and semantic rules. Then we have finally the more complex, the most complex tools offered by provider for a comprehensive data analytic process. These tools embed some components to collect the data directly from the sensors, to manage the data collection, to remove possible noise, to characterize the data themselves coming from the sensors, to store the data, to structure the data collected from the environment in a standard set of repositories according to the nature of the specific data. We can have as sources the sensors, we can have the web, we can have mobile application, we can have a multiplicity of input devices, and the data analytic tools can actually aggregate, combine all of them in a comprehensive view using a standard database or a non-SQL database according to the specific characteristics of the various type of data which are collected. And then we have specifically the data analytics environment, which is composed by a set of tools to organize the data, to distribute the processing eventually on multiple processors if the computation is very complex, in order to reduce the time for the analysis of the data. And then we can have also components for streaming the analysis, so that we can use data which are continuously coming in the system, and we can perform an online data analytics. Finally, these systems based on artificial intelligence provides various tools for visualizing the analysis which have been performed, so that the user can better understand from a visual presentation of the data, of the reporting, what is happening in the application. And then we can have also real-time monitoring components based on artificial intelligence, which take care of analyzing the data which are coming in the system, so that they can automatically detect possible critical situations which have been defined previously according to some rules, or they can define some anomalies so that they can bring automatically this situation to the attention of the staff, of the expert staff responsible for taking appropriate decisions. What is important to point out is that the use of the cloud infrastructure has been a facilitator, an accelerator of the use of artificial intelligence, not only in the cloud, but especially in the Internet of Things, where typically nearby the devices which allow to interact with the environment, the sensors or the actuators, we typically may not have a sufficient computational capability, sufficient storage, in order to perform the detailed analysis and run the appropriate artificial intelligence algorithm. We may not have the capability of storing data, enough data, and to run the machine learning algorithm to configure properly the artificial intelligence techniques for processing this data. Moving this component in the cloud allow to have, in a much more flexible way, the capability of storing and processing the data which are generated in our Internet of Things infrastructure. And we can also use some specific processors which can really boost the computation, allowing to achieve in a very short time, with respect to other regular processor, the results which are relevant in our application. So basically, the Internet of Things infrastructure can be seen as a distributed intelligent processing of our data, where we put the computation, the storage and the computation of our data in the most appropriate component of our infrastructure. If possible, near the edge, near the actuator and the sensors, or the various devices connected to the system, or in the fog or in the cloud, according to the need of our application. But let's see how we can use the artificial intelligence for management. There are many opportunities to increase the traditional approaches based on algorithmic techniques to manage the various aspects, from the beginning of the selection of the functionalities to managing the entire infrastructure. First of all, we have the selection of the cloud and Internet of Things services and components that we wanted to aggregate for our application. And the fuzzy systems has been shown very effective to allow us to define, to specify the resources, the preferences, the operations that we wanted to do, so that we can create a service level agreement in a flexible way, understandable by users who are not expert in cloud and Internet of Things infrastructure. And machine learning can help actually in extracting some knowledge from previous cases, supporting the choice of the users. If we have a cloud infrastructure, multi-cloud infrastructure, if we need to select among the cloud, we may need actually, if we need to select among different type of Internet of Things providers, we may need to understand which is the best match between our needs and the offer. As a consequence, the neural network and the fuzzy systems have been shown very effective to analyze this type of mapping and find the most appropriate one. And in the case of multiple parameters are need to be analyzed, the evolutionary computing and the machine learning techniques have been shown effective in performing the optimization and the analysis of the previous cases. Then we need to distribute the tasks in the multi-cloud, in the cloud federation, in the multiple structure of the Internet of Things, if we have a structured architecture. And also in this case, artificial intelligence has been shown effective to analyze the various offer and to be able to perform the most effective, to identify the most effective solution for our multi-objective optimization. Then when we have a complex problem, we may want to address the complex problem, not rewriting from scratch the entire application, but picking some services which are available in the infrastructure, which are offered by the provider, and connect these services together to build our own application in a much easier way, relying on software which has been already tested by others. The service selection can be performed by exploiting artificial intelligence, in particular by using ontologies, neural networks to perform the matching, and in the case of optimization, we can use the evolutionary computing. When we have identified the tasks, then we need to allocate the tasks on the various processors near the edge, in the fog, if available, or in the cloud. We need to choose where the various activities need to be performed. In a static way at the beginning when we start the application, but we may need to do it also in a dynamic way when the applications are running, since we may have to deal with possible situations that recommend moving one task from a location to another. And also in this case, artificial intelligence has been shown very effective. Then, when we have allocated the task on a specific virtual machine in the cloud, then we need to understand where allocated the specific virtual machine on the host. And also in this case, artificial intelligence has been shown very effective. If we wanted to manage our infrastructure in a flexible and efficient way, we may need to understand when one of the nodes in our infrastructure is going to be, one of the processing nodes is going to be overloaded. And as a consequence, we need to understand when is time to choose if we wanted to leave our application on that processing nodes or move it in another place. For this purpose, we need to predict the behavior of the tasks, the workload for the various nodes, in order to detect when we are entering in a critical situation where the processing and eventually the storage or other activities are on that processor going to be degraded too much with respect to the need of the application. Neural and fuzzy techniques have been shown effective for this prediction. When we detect to detect the need of performing a load rebalancing in our architecture and to start the dynamic reallocation of tasks based also on the prediction of the workload, we need to choose which are the components that need to be moved, the activities that need to be moved, in order to achieve a more appropriate balance in the workload. And we can do this in two ways. It can be a reactive way. In this case, we need to have a monitor which observe the behavior of the various processing nodes and take into account when they are reaching the limit of their capability in order to satisfy the specific application, or we can work in advance in a proactive way, so that by using the information provided by the predictors of the workload and the behavior of the tasks, we can actually in advance, before reaching the critical situation, we can choose to reallocate a part of the tasks in order to remain in a condition which is much more effective for our application. And neural and fuzzy techniques have been shown effective in this perspective, and the evolutionary computing has been shown effective to perform the optimization, the multi-objective optimization when we need to do the reallocation. Similarly, for the management of the Internet of Things infrastructure, we need to consider the allocation of the various tasks, the various functions in the Internet of Things structure, as well as the possible dynamic reallocation of the resources to the tasks due to the evolving operating conditions in the system. Also, in this case, we can perform a prediction of the task behavior of the workload that we have in the various components of the Internet of Things infrastructure based on artificial intelligence techniques in order to start the rebalancing of the workload. And as a consequence, to ensure a dependability of our architecture due to the workload in the system. We have also another aspect which is very critical in Internet of Things infrastructures, the energy management. We need to ensure that the operation of the system is working properly from the application point of view, is working on time, so is generating the desired output, in the due time, especially if we have real-time applications. But we need also to minimize the overall cost of running the infrastructure. As a consequence, we need to be really careful for the energy management, since we need to ensure the sustainability of the operations. Energy prediction is, as a consequence, very important in this infrastructure, so that we can choose where to allocate the various components by taking into account the use of the energy and the predicted use of the energy. The artificial intelligence has been shown very effective to perform this prediction, and machine learning has been shown very effective in order to understand the previous situation and extract some knowledge from the previous cases. When we have these very complex infrastructures, we need also to configure the infrastructure in the best way as possible. We need to design the infrastructure in the best way as possible by considering which are the components that are needed to support an effective management, an effective operation of the entire infrastructure. From the hardware point of view, we need to ensure that we have sufficient the components in order to guarantee the continuity of operation even in the presence of faults, even in the presence of possible security attacks, at least under given models, so that the application can continue to use the application. So we need to introduce a sufficient redundancy in our architecture. And we need to consider also that we need to choose which components are needed, which needed, how the architecture needed to be expanded in order to satisfy the performance needs of our applications. And we need to understand how to structure, how to optimize our infrastructure, also in order to create a sustainable infrastructure for a sustainable environment by managing properly the energy. Artificial intelligence has been shown effective in the literature and in the industry to address all these aspects. In addition, it's important to be able to manage the faults as best as possible in this architecture, both in the cloud infrastructure and the global Internet of Things infrastructure, since we need to ensure resilience, we need to ensure the continuity of service, even in the presence of faults. So we need to be able to have sufficient hardware redundancy in our architecture in order to allocate the operations so that if one component is failing, the other is actually able to continue to provide the service. In this example, we see that the same task, a task has been duplicated and allocated in two different processing units so that if one is failing, the other can continue to support the application. And we may need to have a dynamic reallocation so that when a part is faulty, we can continue to provide the same fault tolerance capabilities by reallocating one of the activities in another node. But we need actually to act in advance. So we need to minimize the possible disruption by considering that we can predict possible faults, possible critical situations, and as a consequence, act in advance by performing the reallocation. In these activities, the artificial intelligence has been shown effective both for the mapping and for the prediction. Security is the other important aspect for the Internet of Things infrastructure, since the Internet of Things infrastructure is connected to the worldwide internet. And as a consequence, we need to ensure that we are detecting possible intrusions, we are detecting possible malware in order to confine these critical situations in the node that has been affected and eventually remove it. Neural network, fuzzy system, machine learning have been shown effective to perform the classification and the clustering of security pattern in order to support this analysis. And they have been also effective in classifying the trust of every component so that we can choose when we build our application to use specific nodes with a trust level which is higher than a given threshold that we want according to the criticality of our application. Then we need to ensure in this kind of complex architecture the analysis of possible threat, the prediction of possible security breaches, and artificial intelligence has been shown as very effective in analyzing in a flexible way the data that are collected in the logs by the system and by the network and detect possible threats due to the security attack, due to various security vulnerabilities that we may have. And they have been also shown effective to predict the level of security of the various components so that we can choose which are the components that we want to use in our application if we need to ensure a high level of security and privacy. For observing this very complex architecture, is necessary to have tools which are helping us as managers in observing quickly what is happening in the entire infrastructure. Due to the complexity of the infrastructure, it's not feasible that we have to observe every specific data coming from the various components, every specific information about the working status of each specific component. So we need to have a filter which is observing what is happening. Sorry, some mistakes occurred and I have been muted. I am continuing now. As I said, we need to have a tool which is able to observe what is happening and filter the data so that only the critical information are brought to the attention of the staff monitoring the behavior of the system so that they can take quickly an action for the very critical situation. And fuzzy and neural networks and machine learning have been shown very effective in detecting possible anomalies and bringing them to the attention of the monitoring staff. The cloud pricing, the Internet of Things pricing is also very important, and the dynamic analysis of the offer on the market and the request of the users actually helps in setting the best price so that we can keep the price low and make the customer sufficiently happy without losing customers if the price is too high, or without losing sufficient revenues to support the company offering these services. So the basic contribution that I like to bring to your attention today is the fact that the Internet of Things infrastructures are an opportunity to provide intelligence to the applications in a seamless way, in a structured way, but they need also more intelligence in the management. And artificial intelligence, in particular the computational intelligence, have been shown very effective in this perspective. Thank you. If you have any question, I will be very happy to answer.
If the participant wishes to ask any question, they can either write in the chat message or they can unmute themselves and ask. হ্যাঁ স্যার, সিদ্ধার্থ স্যার কিন্তু ইয়েতে নেই, সেশনে নেই। আপনি আই থিঙ্ক স্যারকে ইয়ে করে দিন, মানে কেউ তো কিছু জিজ্ঞেস করছে না, এই একজন জিজ্ঞেস করলো সবে। দাঁড়ান আমি কোয়েশ্চেনটা ফরওয়ার্ড করছি। আপনি কি করবেন ওটা? ইয়ে তো শো করেছে বোধহয়, সৌরভ স্যার, দুলাল স্যার বোধহয়। সিদ্ধার্থ স্যার মানে আমাদের সেশন চেয়ার এখন সেশনে নেই। তো সেশনটা
I see that there is a question in the chat now. Maybe it took a while to type it.
the question is, how do you think deep learning is related to IoT?
Yes, thank you. I'm seeing the chat. Thank you. Well, deep learning is one of the techniques that I collectively named as neural networks. Is one of the structure for the neural network. So is absolutely one of the techniques that can be used in for Internet of Things. When I say the neural networks, I mean not only the more traditional techniques, the feed-forward, the multi-layer perceptron, but not only the other techniques, the self-organizing maps, the old traditional techniques, but I include also other techniques like the support vector machines, the radial basis functions, Bayesian networks, and in particular, and the more modern solutions based on convolutional neural network, deep learning, all these type of computing models for neural network. Deep learning is one of the neural networks techniques that are used, which are explored more and more nowadays.
Any other question, please, from the audience to our respected Professor Dr. Vincenzo Puri for any other question? Oh, yes, it seems that there is no question. Thank you, sir. We are delighted and glad to get you, and we are very skeptical because there is a difference between time frame of your country and our country. But we are very much grateful to you, sir, for your nice deliberation and lecture. Sir, this is the certificate.
Thank you for the invitation, and really appreciate. I look forward actually to visit you and Bangladesh as soon as possible. Thank you.
Yeah, thank you, sir. Thank you, sir. We are delighted. We are glad to know, sir. Sir, we hope to meet you again physically one day, sometime, somewhere, because world is a very small place.
But it will. I will be very happy to visit the entire area, India, Bangladesh, since I always received a very good welcome from the heart from people there. Thank you.
Yes, sir. Thank you, sir. Sir, stay safe, stay healthy, sir. In this pandemic condition, sir, we hope that your health is well and will be well, and we hope to meet you again in any physical or in a virtual meet.
Thank you. I look forward to.
Thank you, sir. Thank you once
Thank
again.
you. Thank you.
Thank you. Now we move
Have a
on
good
to
day.
the next keynote speaker. So in between there is a 5 minutes break, and then we'll once again we'll meet. And our next keynote speaker is Professor Dr. Michael Gerard Hinche. He is the President IFIP and the Director Irish Software Engineering Research Center, University of Limerick, Ireland. And his session chair, Dr. Nilanjan Dey of JS University, and Dr. Devdatta Sinha, former head Department of Computer Science in Calcutta University. So I request Dr. Nilanjan De or Dr. G.D. Sinha to take charge of this session. Tufan, make them co-host and unmute them. Tufan, our support service team, Tufan,
Yes,
kindly make Dr. G.D. Sinha and Nilanjan De
Krishna
co-host.
sir has already been made co-host.
Okay.
Lanjan sir is currently not in the session. Mike Hinche sir is also present and has been made co-host. Sir has also shared his screen, as we can see.
I am Professor D.D. Sinha, present in the session right now. Hello, I am
Yes.
audible?
Yes, sir, you're audible.
I have not received a formal biodata of Professor Hinche, although I know him personally because he happens to be here for quite a long time, different sessions, different conferences, and I know him. So
Sir, I'm introducing Professor Dr. Michael Gerard Hinche.
okay,
Michael
thank you,
Gerard
Aniruddha.
Hinche, a respected guest, is an Irish computer scientist and former director of the Irish Software Engineering Research Center, Lero, a multi-university research center headquartered at the University of Limerick, Ireland. Mike Hinche studied at the University of Limerick as an undergraduate, Oxford University for his MSc, and Cambridge University for his PhD. Hinche, our respected guest, Professor Hinche, has been a promulgator of formal methods throughout his career, especially CSP and the Z notation. He was director of the NASA Software Engineering Laboratory at NASA Goddard Space Flight Center and is the founding editor-in-chief of the NASA Journal Innovations in Systems and Software Engineering, launched in 2005. He has held many academic positions, both visiting and permanent, at a number of universities, including the University of Nebraska, Queen's University Belfast, New Jersey Institute of Technology, Hiroshima University, the University of Skövde in Sweden, and was at a Loyola College in Maryland, now Loyola University, Maryland, United States, before his current post. Professor Dr. Hinche is a member of Academia Europea, a fellow of the EAIT, a fellow of the IMA, a senior member of the IEEE. He is a chartered engineer, chartered professional engineer, chartered
Aniruddha sir, you have been okay.
Now, Dr. D.D. Sinha, kindly continue.
Yes, Professor. I request now Professor Hinche. I do not know the title of his talk, but I think Professor Hinche is a worldwide famous computer scientist. So I request now Professor Hinche to deliver his talk.
Thank you very much. Thank you for that very kind introduction. I think I recognize some of it from Wikipedia, but thank you very much for that. It's a great pity that we're not there together in person. As you know, I visited many times, as you said, and I've enjoyed meeting with everybody. And as Vin says, the support and welcome is always fantastic. So we're always glad to visit our friends. So thank you, Professor Sinha, and thank you, Professor Day, for your introduction. So the title of my talk is there anything that isn't software? And as I'm a software engineer, you might find that I'm a little bit biased, so you may not be terribly surprised at my conclusion. So I'd just like to remind you of how young our discipline is. We tend to forget that, you know, in dealing with computer science and dealing with software, even electronic engineering, we're not dealing with the long history that people have in physics and chemistry and biology and so on. So on your screen right now, you see a picture of EDSAC, and this is the state of the art in 1949. And there isn't a random reason why I chose 1949. I chose it for a very specific reason, because this was not the first computer. It was not even the first electronic computer, but it was the first computer to execute a stored program. And that was significant because it meant that software now came into its own. Software now became a major issue, and software could change. That means that the execution of the program could be changed as it ran, not just on the basis of inputs, but on a number of different factors. So this meant that from this point forward, software became a major determinant in the execution of a system. Just to give you an idea of what it was like, 650 instructions per second, 1,024 17-bit words, paper tape input and output, 6,000 valves, 12 kilowatts of power consumption, and it occupied a room of about 5 meters by 4 meters, and it needed about 4 times that space around it just for ventilation and cooling. In 1951, 2 years later, the British government did a survey, and they determined that they would only ever need 3 of these machines. So if you have one of these in your pocket, you have far more power than 3 of these machines in your pocket. But in 1951, they thought they would only ever need 3 because they would only ever use these machines for scientific calculations. In fact, it was in 1958 that the first use of a computer for a business purpose came about, and there is a connection to India. In fact, we are planning to have an IEEE milestone event which will record the fact that the first use of a computer for business was in the UK in 1958, but the company was Lyons Tea, who were importing tea from India and using a computer to catalog their inventory. So that was the first actual business application of a computer. Many people consider this to be the first computer, and the gentleman in the bottom right is the gentleman who invented it, Charles Babbage. You probably have many times heard the name. Even school children have heard the name because his 200th anniversary a number of years ago, there was a lot of emphasis on his name. He built a machine called the difference engine, and he built parts of it, working parts of it. It's claimed that had he had access to the manufacturing that we have now, in the sense of being able to make cogs and wheels that were much more accurate, then his machine absolutely would have worked. As it was, it worked to a certain extent. And the parts of it that he built were quite huge. So if you look at the picture on the left, on the top left, the gentleman in the picture is Doran Swade, who's the former curator of the Science Museum in London, and he's about 6'4" tall. So that gives you an idea of how big this small part of the machine is. People think that Babbage set out to build a computer, but he didn't actually set out to build a computer as such. What he did was set out to solve a very specific problem. And this is the problem, that the tables used in the shipping industry, particularly logarithmic tables, were prone to so many errors. So here you see a correction of an error in 1832, and a correction of a correction of a correction in 1833, and a correction of a correction of a correction of a correction in 1836. So these tables had so many errors. Ships were lost at sea, cargo was lost, lives were lost, a lot of money was lost. It truly was a critical application, safety critical application. So this was Babbage's intention, was to solve this problem, and he figured that if he could compute these tables automatically, then he would solve most of the problem. In fact, he also had the idea of being able to print these tables automatically, and he had the idea of using brass cogs with numbers in reverse that would push against paper, and then he would scatter ink across the paper. So it's not terribly different, conceptually at least, from what we do with laser printers. So he really was ahead of his time. And of course, with the arrival of the first computer came the first computer programmer. And we use this example, of course, to encourage girls into STEM and STEM careers, because she was Augusta Ada Byron, the daughter of Lord Byron. She married Lord King, who ultimately became the Earl of Lovelace. So she was the Countess of Lovelace, and we know her as Ada Lovelace. And she was fascinated by Babbage's machine. She understood that she could do lots of things with it, more than just calculating logarithmic tables. She was very educated, particularly for a woman of the time. She had learned mathematics from De Morgan, and she was very interested in solving problems. And so she did use Babbage's machine to solve a number of mathematical problems. She wrote out some of these problems on pieces of paper. She understood that she could reuse some of the steps in calibrating the machine, and she wrote these on separate pieces of paper and reordered these pieces of paper. So while Babbage came up with many of the ideas that we still use in von Neumann architectures, he came up with the idea of cache memory and so on long before we had electronic computers. But she came up with many of the ideas that we still have in computer programming, like the idea of having subroutines, like the idea of software reuse, etc. So these days we see software used in just about everything. Normally we would be traveling to meet each other, and we'd almost certainly be using software in everything from flights to trains, even down to bicycle and scooter rentals these days. I actually had a very interesting application of IoT yesterday. I'm currently in Ireland, but my car is in Washington, DC, which is about 3,000 miles away. And I got a message yesterday from my car telling me that the battery was critically low and it needed to be started, and to please start the car. Wonderful application of the IoT, where across thousands of miles I get notification of something that I need to do. Continuing with cars, I have a colleague who's obsessed with getting rid of traffic lights and the idea that cars should all be talking to each other, whether we have automated driverless cars or not. Cars should be talking to each other for safety purposes and for control of traffic, etc. I tell people I live a little over 200 kilometers from Dublin Airport. There is one set of traffic lights between my house and the airport, and that's at the end of my street. We're determined to get rid of them. And of course, the last few weeks and months, we've had a lot of interest in space exploration, highly dependent on software. We've had the very successful landing in the last week of the Perseverance robot on Mars and the wonderful pictures it's sending back. We have a number of countries, including India, with now missions to both Mars and the Moon, unmanned primarily, but there is a plan to send people back to the Moon and ultimately onto Mars. And there you see an illustration of the Artemis mission, or Ares as it's often known, named after the Greek god of war, equivalent to Mars, and Artemis, of course, being the Greek god of the moon. So we've seen software be used in all sorts of manufacturing. We already have Industry 4.0 upon us, and people are already talking about Industry 5.0 and how that will be another game changer. We've seen power production, we've seen telecommunications, and unfortunately in the last year, we've seen how healthcare is driven by software, how software is both diagnosing people's health and health conditions, and how it's also being used in their treatment and in the tracking and tracing of people who are infected and spreading disease. We do a lot of this based on our simple smartphones that many of us have in our pockets. We use software for all sorts of transactions, whether it's buying online and having food delivered to us, which many of us are doing these days, and doing all sorts of transactions in terms of shopping, banking, etc. And of course, that leaves us open to the possibility of cybercrime, which has again become a big issue in the last year and a big concern for many of us. Indeed, you may remember in the middle of the year last year, there were a number of hacks into Twitter accounts. So these are not just fake posts, they're actual hacks into famous people's accounts. It wasn't just Barack Obama, it was also several other politicians and Hollywood actors, etc. We'd like to think that most people who would be fooled by this don't have enough ability to go and actually buy the Bitcoin and send it. Therefore, they probably weren't a serious risk at this attack. But the point is that the attacks were there. And so cybersecurity has become a big issue for us in all sorts of technology. And of course, the Internet of Things gives us so much more opportunity for our information to be shared, for our information to be available to all sorts of people, and of course, unfortunately, for that to be misused. This year, of course, we are concerned very much with health, and health has been a big issue, and it is one of the Sustainable Development Goals of the United Nations. You know these goals, which are aiming to be achieved by the end of 2030. Each year, the United Nations identifies a number of the goals that it will prioritize. The priority list for 2020 was generated in July 2020, and it did not include number 3, which is good health and well-being, which the United Nations says is about health monitoring via emerging technologies. And of course, we see the Internet of Things as being a major emerging technology, particularly in this area. We're concerned with remote contact diagnosis and treatment. So being able to talk with people remotely, being able to diagnose their situation and provide treatments to them, much of this remote. We're looking at population and disease monitoring, and again, the Internet of Things has much of a role to play in this, because we can identify the population spreads and population growths and how disease is spreading through those populations. So we have to prepare for disease outbreaks by identifying symptoms, following treatment protocols, and performing remote diagnostics, and then help analyze these trends and make projections about disease outbreaks, the health service usage, and patient knowledge, attitudes, and practices. So all of these things, of course, are highly dependent on technology. And some of the technology we're using is more basic, but a lot of it is nowadays been based on the Internet of Things and the advantages that gives us. So these things in red are exactly what we are trying to do with our technology. And in many cases, it's based on the humble phone, smartphone that you have in your pocket. So ultimately, we see ourselves having this cyber physical social system where the entire world is interconnected, where everything we do is interconnected. Our cars talk to each other. We're entertained in our cars. We talk with our friends in our cars. Our cars talk to smart highways, which know where we are. They understand the traffic flows. They understand where there are going to be pileups, where there's going to be traffic jams, where that needs to be resolved. And of course, we see our healthcare becoming global, that we have access to our healthcare everywhere, that the simple phone again in our pockets is carrying much of our data about us, and that data is available. So it's a cyber physical social system because of the cyber aspect, that we are reliant on software to pull all of this together and to make all of this possible. We're concerned with the physical world because we're measuring where we are, where other things are, where we are in relation to various people and places. And there's the social aspect because we're sharing all of this information with our friends, but we're also sharing it with organizations and the big tech organizations like Google and the social media, and indeed even people like Amazon, who know what we buy, where we buy it, where we want it sent to, etc. So we're giving this social dimension all of our information. Much of it is good because our friends know where we are and what we're doing and what we're up to, but it's also giving away a large amount of our privacy and our personal information to people who will use that against us. And so some of it will be done in legal ways, where they will use this information to sell us things, to understand what things we're interested in buying, when and where, but also to misuse that information to try to con us into buying things we don't want, to sending money to people that don't deserve it, and using our information against us, primarily for fraudulent reasons. So it is becoming this one large cyber physical social system. One of my colleagues did a survey with the University of Cambridge a number of years ago, looking at the various industry sectors that build software. And of course, we know software is an absolute necessity in a number of areas, but we don't tend to think of it as pharmaceuticals. Maybe we do nowadays as we see vaccines being rolled out and what happens when the vaccines are not being prepared in time. And a big issue now, of course, becomes the distribution of these vaccines. But it's also a critical skill in all sorts of areas, from financial services to medical devices to transportation and even construction, things that we don't necessarily think of as being software based, but indeed it is. So this is a chart. It's a bit out of date now. It just shows some of the companies that we in my research center deal with. And some of these, of course, are household names that you'll recognize, like Intel and IBM. Some of them may be less recognizable to you, like United Technologies. They are a huge US-based organization that owns Sikorsky helicopters, for example, Otis elevators, Carrier air conditioning, and focuses very much on smart buildings. And some of the others around the outside you may not recognize, but in the US, for example, everybody knows Fidelity. Fidelity is actually the largest privately held company in the world, and it's an investment firm. And in fact, in the US, typically all professors have a choice between Fidelity and TIAA-CREF for their pension plans. So academics know Fidelity very well. But you see a whole range of different areas, from very small companies to very large companies, concentrating in completely different areas. So we are in a situation that we do actually have software absolutely everywhere. And software is the leading factor in everything from cloud and big data and data analytics through to cyber physical systems, multi-core, smart infrastructures, and so on. And it's used in everything from ICT itself, of course, to medical technology, to financial services, to manufacturing, to automotive. This chart on the bottom right might be a little bit confusing because it's using two different scales. But what it says is that around about 2013, BMW, the car manufacturer, became a software company because it was employing more software engineers than any other form of engineer. So it just transformed to being a software company. And they estimate that there are 1.3 instances of all BMW cars. So everything is so customized, not just physically in terms of colors and materials, but with the software, that everything is so customized, there are no two cars identical. And indeed, many of the car manufacturers are now downloading software updates as much as every other day to their cars. Mostly it's still for things like entertainment and GPS systems, but it's moving to other things like the braking systems and so on. And as I gave you the example yesterday of my own car, which was very, very useful to save a situation where it wouldn't restart. And on the top of this slide, you see a quote from the Vice President of Research of Analog Devices. Analog Devices is one of the largest chip manufacturers in the world, and they happen to have a large facility on our campus. And the Vice President for Research, who didn't want to be named, but it's easy to figure out who he is, said, our company has become a software company. The problem is our engineers don't realize it yet. So they don't realize that as a chip manufacturer, they have become a software company. But building software is not simple. We tend to think it is. We hear the stories of 14-year-olds in their bedrooms writing apps and making millions. And of course, that does happen. But in actual fact, building software that is highly reliable and works as it is supposed to is a big deal. And coding can be as little as 7% of the overall development process. So as we look at more and more complex software, we see the importance of doing it well. And there's a big correlation between how good our software is and the business benefits we get from it, like improved time to market, improved quality, improved productivity, and of course, compliance with all sorts of regulations. And we've heard of the famous examples of software going wrong and how expensive it can be. So the recall of the braking system for the Toyota cars is estimated to have cost them about $3 billion US. And the Mars orbiter failure, for example, where it crash landed onto the surface of Mars, is estimated to have cost about $655 million. But that's just in physical costs. Think of all the years of work and effort that were put back because of the loss of the device. So software isn't static. We have to realize that software does change. So we have legacy systems that are brought together over time, combined over time, because organizations merge or take over each other. We have new software and software technologies being used, and we decide to make changes to our software to focus on new technologies like the cloud, like the Internet of Things. And of course, then we have new requirements from our customers who are looking for more and more features, more and more interaction, more and more cute things to do. Some of them are necessary, some of them are not. And then, of course, there are requirements for regulation, etc. But my own interest is in software that adapts at runtime. And so that is software that has to change because of things that happened in the environment that we couldn't truly have predicted or planned for, and meet the fact that there are changes being imposed upon us that we didn't know about. And of course, protecting the system in the long term so that it will run even in the context of external threats. So as one of my colleagues says, software is supposed to change, otherwise we do it in hardware. And that is true, because historically, we're much better at developing hardware than we are developing software. So just think of the number of applications and the size of applications that have been developed in software. So this chart is quite old, it's from April 2009, but it gives a nice overview of just seeing the amount of software that's being developed and how much code is involved. So look at even cheap mobile phones, how many there were and how much software is involved in them. And that's before we moved to smartphones. So think of what it is like nowadays. And then, of course, the size of the software, how we saw it grow. So obviously, the red diamonds here are space flight control. And you can see that increased dramatically from the 50s up to recent years. We see switching systems growing. That's the blue squares because of the growth of the internet. But the interesting one, again, is automotive software that grew dramatically. So in the early 1990s, there was virtually no software in cars. Nowadays, many cars have especially high-end cars have about 70 processors, all running software, all talking to each other over a CAN bus. And the car is becoming a software device. So we're interested in critical applications. So systems, if it fails, we can have significant negative consequences, where we have strict requirements on security and safety, because we have to make sure that people are safe and that the environment is safe. But more and more critical is applying to the organization's competitive advantage, the fact that the software gives the organization an advantage over somebody else. So why do we go to Amazon to buy books and DVDs? Well, we buy from them because they have a great selection. But why do small companies go to them to sell their products? They go to them to sell their products because of the value of the software and the platform that's provided by Amazon. Something similar with Uber and Lyft. These individual drivers, I know the situation there is going to change because of recent court cases, but individual drivers are, of course, earning their living by driving people around, but they're using the platform provided by Uber and others to identify the customers and to where they want to go to. That application has become critical to the existence of the organization and why one organization is more successful than another. So we're in a situation that we have a lot of software that's widely used, and often we don't even know it's there. We tend to forget that there's software in so many things, and certainly the general public don't realize how much software there is in so many things. There's an awful lot of legacy code that's very badly structured and very badly maintained, and we've seen examples of software failures because of changes made to the software that weren't done in a regulated manner. And we're in a situation where we have software used on diverse platforms in complex situations. And basically, we just don't have enough good quality developers and testers. And we need to understand that software has to change, software development has to change. A lot of new approaches, of course, are making a lot of sense, but we still have a long way to go, and we can't get away with doing the same thing as we did for the last 50, 60 years. So we're interested in software that's evolved from legacy code and legacy systems. So the oldest software is actually owned by NASA. It's from the Voyager missions, so it's now gone interstellar, but we believe it's still to be running. We have software that's built as a result of combining component-based systems or parts of systems over periods of time, essentially that an organization adapts its software to keep it running. We've deliberately changed our software to exploit new techniques and new platforms, again, like the cloud and IoT. And we want software that adapts at runtime, again, in order to meet changes in its environment that we couldn't have planned for and that may be a threat to it. So we've been working on this in a number of areas. We've been looking at smarter cities. So we've been working with Intel and IBM and Dublin City Council, and also Cork City Council. Cork is the second city of Ireland that tends to have flooding in January, February every year. And as a result, traffic routing has to be changed. There has to be changes to the way traffic is allowed to go through a city. Certain roads have to be closed, etc. But it might also be because we want to do that because a specific event is on, there's been a fire or damage to a roadway or roadworks, for example. And we've been looking at how we can make our cities smarter. And like I said, one of my colleagues wants to get rid of traffic lights altogether. I think we're away from that, but we will get there eventually. We've been using software product lines to get efficiency from various levels. So we've been working with one company that I'm not allowed name who bids for government contracts, and they need to have their bids be so accurate and so detailed. And we've been able to use software product lines to reduce the time it takes them to prepare a bid from about 6 months down to a few weeks. The big advantage of this is that they have to have their accuracy very, very high. If they price too much, they won't get the contract. If they price too low, they don't make money. So we've had great successes with that. I already mentioned United Technologies. We've been working with them and IBM on adaptive security and privacy, how we can change privacy settings in the cloud, how we can give people different privacy situations and different protections depending on where they are, what they're doing, what building they're in, and what other assets are in a building at the time. We've looked at parallelizing code to make use of multi-core technology. So we work with a company called Movidius that you've probably never heard of. They were bought out a couple of years ago by Intel, so the name has more or less disappeared. But they make a chip that's used in absolutely every smartphone. So if you have one of these devices, you have a Movidius chip. And we've been able to help them move much of the processing into a camera. So we've been able to develop multi-core based smart cameras. So the camera can identify people, the camera can identify number plates on cars without having to send all the data back to somewhere for processing. And of course, this makes the Internet of Things so much better because we don't have to have the overhead of sending data back to somewhere to process it. We've been working with a number of organizations on architectural recovery and preservation, so improving the structure of their software. So we've done a lot of this with financial services companies. And as you might imagine, financial services companies tend to have old software that's evolved over time that has to change to meet various types of regulations, but then is also the subject of takeovers and mergers, where everything has to go together. We've worked with one company that does floodplain mapping, and we've had great success in that because we've been able to increase the accuracy of their maps, but we've also been able to avoid the architectural drift, where the system just deviates so much from what was originally planned, and as a result gets so inefficient. And in that same context, we've been looking at performance evaluation in a number of large-scale systems. So we've worked with IBM, for example, on their server farms, where we can actually identify and automatically deal with a large number of problems. And those problems that we can't deal with automatically can be flagged and triggered. And we've actually had a very successful startup company out of that. And my own area has been on developing autonomous space systems. I've been developing that with NASA and also with the European Space Agency, and also an EU-funded project called ASCENS. So one of the things we've been doing is using swarms of intelligent spacecraft to go to the lunar surface and ultimately to Mars. So we're talking about sending devices that will collect as much data in a few days as the Mars rovers have in all of their time on the planet. We're looking at going to the rings of Saturn, and we're also looking at going to the asteroid belt. As you know, NASA has a plan to put a human on an asteroid, and that's why that is one of the interesting missions for us. So these are the sort of devices that we would use to do that. Again, this is a physical device, but it's entirely dependent on software. So each of the nodes is a computer running software, and control of the device is by transferring control from one node to another, and then basically it falls over. This means it can go over rocks and craters and over rough terrain. And we can connect a number of these together to make something like a caterpillar or a centipede, and that then, of course, can carry other devices. So that looks very good in theory. Here it is in reality. So it doesn't go as smoothly as in the animation, but of course it has more gravity to contend with here on Earth. This device can shrink down to be a 30-centimeter cube, can expand out to be 2 meters tall, and it can climb the outside of a 5-story building. So this will be the basis of a number of missions, and this is one of our concept missions called PAM. It's a concept mission because it hasn't launched yet, and a lot of the ideas that will be used in other missions in the meantime. NASA missions are usually planned 20 to 30 years in advance. So we're looking at this launching, it was originally to launch this year, or last year rather, and now we're looking at 2030. But the idea is to launch 1,000 small spacecraft from L1, which is the Earth-Moon gravitational point, and that these will be pulled by gravity into the asteroid belt, will form themselves into a number of subswarms and collect data from various asteroids of interest. But the interesting part is that this arrow here marked 5 is unidirectional. So the data is sent back to Earth, but Earth has no control over this mission. It's so far away that there's a 40-minute round-trip delay. So if the mission sends a message back to Earth saying I have a problem, even if Earth can send the necessary instructions with no delays, by the time the messages get back, there's been a 40-minute round-trip delay. So one of the devices sends back a message to Earth saying I'm about to have a collision with an asteroid. What do I do? By the time Earth sends the instructions, the whole mission is lost. So this has to be completely self-managed in space. So although it's physical devices collecting data from various asteroids, it is doing all of this based on software. It's making its own decisions about what it should do. It's making its own decisions about which of these asteroids are of interest, which ones it should pursue, where it should go and what it should do. And it's also reprogramming itself because as devices are damaged, they're not able to collect data anymore, but they may be able to relay data back to Earth. So this has gotten a lot of interest in all sorts of scientific publications. You see here an article from back in 2010 in New Scientist. The Times of London gave us a full-page coverage of some of the technologies we were building. Unfortunately, some of the Space Geek websites misunderstood what we were talking about doing and thought we were building something that could be used as a weapon, which is not the case. In fact, a lot of the technology is based on a patent that we got based on some of the work we had done. And my mom, my late mother, who at 81 got her first patent, I overheard her talking on the telephone to one of her friends, telling her what I do and why software was important. And what she was telling her friend didn't make a lot of sense until I thought about it and thought we could actually adapt some of this. So we did. It's received a number of patents, and those patents are licensed to NASA and are being used in current and future space missions. So our contributions have been in 4 areas: formal methods, autonomic computing, software product lines, and automatic code generation. So we've looked at how we can specify these kind of systems and what we would want them to do and what kind of constraints we would have on the decisions they can make. So we have essentially a dashboard of different notations, everything from CSP that deals with concurrency to X machines, which deals with data and state changes, to a probabilistic version of CCS, which deals with probabilities and the likelihood of certain things arising. One of my postdocs has developed a language called ASSL, Autonomic System Specification Language, and that has the advantage of having a number of primitives built in that we would need in these sort of missions, but it is fully formal, so that means we can make proofs about its behavior, and we can also generate Java code. Now, NASA doesn't fly Java code, but the point is we can still generate an implementation. We've been looking at how autonomic computing can help so that we can get inspiration from the human body. So the sympathetic nervous system is concerned with the fight or flight. So that's protecting the body in the short term. An example is if you touch something hot, you automatically pull your hand back. It's the way your body protects itself. And then, of course, there's the long-term health of the body, the rest and digest. So from this, we can build up an autonomic environment. So we use the idea of a heartbeat, such as you would have in embedded systems, to show a component is working. We can add to that the concept of a pulse beat, just like the human body has a pulse that tells us different things about the health or the state of health of the body. NASA's been using this for about 50 years. They've called it beacon monitoring. And the idea is that you send different signals corresponding to different states. So you have a slow, steady signal that everything is working well. And then you have a fast signal if there's a problem. We can put components into sleep mode if they're damaged or not working correctly, or if we're suspicious about whether they're a danger to the system because they may be a cyber attack. We can allow those components to wake up again when they're ready to work or when we've determined that they're safe to use. And then we have what we call an ALICE signal or an autonomic license that allows us to negotiate between components that will work together in a particular mission. We've been using feature models from software product lines to change the functionality of these systems because we want to send these devices to the moon and to Mars. We want to send these devices to the asteroid belt and to the rings of Saturn, but there are different issues for protection when we do that. So here in red, we have the self-protection component of dealing with the solar storm. So when the sun ejects junk and radiation, we need to put the devices into sleep mode and then take them back out of sleep mode when the danger has passed. When we go to the rings of Saturn, we have different issues. So we can swap out this functionality and swap in different functionality. And we want to do automatic code generation. We want to take the requirements that NASA engineers tend to express as scenarios, or nowadays maybe UML. We want to build models from which we can generate code. And from code, of course, we can extract models using existing reverse engineering tools. We can use the mathematical laws of concurrency and reverse them so that we have round trip engineering. We can go from requirements to models to code and all the way back again. So we're in a situation that we have demand for large complex systems. We're trying to do smart everything from smart grids and smart cities to smart buildings. Everything is totally connected and software intensive. So the IoT, of course, is a perfect example of this push. We have systems everywhere that are competing for resources and not just data. We have so much code that we do need to have self-managing software. We do need to have software that can manage itself and keep functionality going. So we truly are becoming a complete cyber, physical, social system. So my question to you at the beginning was, is there anything that isn't software? Well, I warned you I'm a software engineer, so my opinion might be biased, and I would say no, but we'll be a little bit more discreet and we'll say no, not really. So thank you very much indeed. Again, it's always a pleasure to join you, and thank you for the invitation, and I hope you enjoy the rest of the event. Thank you.
Thank you, Professor Hinche. I would expect some questions from the audience.
Absolutely, happy to.
Oh. So is there any question from the audience? Not responsive. So
Okay.
I feel I have one
difficult.
I have one question to you. Not really question. I want to have some idea about the adaptability of softwares, like the agility of softwares.
Mm-hmm.
How do you think? How do you think like that in future?
Well, I think the problem is that there's always been this belief that because software can be changed, we should change it. And indeed, that is the big advantage. As I said, you know, one of my colleagues, I quote him, if we didn't need it to change, we'd do it in hardware. So obviously there's big advantages of being able to change software in a device that's in space without having to bring it back down to Earth. There's a big advantage of being able to change software in for example, a pacemaker. So a patient doesn't have to go and have surgery just to update the software. But as we saw with the example with the Vice President of the United States a number of years ago, that means it's open to hacking. So we have to have an ability to change software, but we have to make sure that that ability is not taken for granted and abused. We have to make sure that the software is changed sensibly and reliably and controlled. So yes, it's a big advantage for people being able to make their own changes, but they don't always make sensible changes, and they don't necessarily make changes that can be released to other people, because the change suits their organization or their situation doesn't mean that it works for everybody else. So I think, of course, we want to be able to change software, but we have to be able to make sure that it's done in a controlled way and it's done in a valid and safe way. So there are, of course, a number of approaches to doing that, which will ultimately win out. I don't know. I think there'll always be multiple approaches and multiple different ways of doing it. But it is important that people know that software can be changed, and that if it has been changed, it doesn't necessarily perform the way it did in the past. As you know yourself, software on your smartphone gets updated. You're normally told an update is about to happen or an update has happened. But of course, the way your phone works afterwards can be quite different. Now, that's not anything malicious, but of course, it could be something malicious, or not even malicious. It could just be something that was not well planned. I would expect that downloads from Apple and other manufacturers are going to be planned and sensible, but we might not always be in that situation. So we need to be careful that we do allow agility, but also we have version controlling, and we have sufficient warning to people that because software has changed, it may not function exactly as it did before.
Thank
I
you.
hope that makes sense.
I now request my co-chair, Professor Nilanjan De, to say something. Are you there, Professor De?
I'm here. I'm here only. Hi, Mike.
Oh, yes.
Hello, hi Nilanjan.
How are you?
Good, how are you doing?
Yes, I'm fine. So actually, I'm a little bit late today, but as per the schedule, it was 3:15. So I think
We started a bit early.
Yes, sir. No problem, sir. I was attended the full talk, so
So
I saw you there from the beginning.
You'd
Yeah,
like to comment on this? Please have a comment on this, on his lecture.
Sir, comment is basically for this particular talk. I mean, I have heard multiple times, because I know Mike for a long time, and we have, I mean, many times we have attended some similar kind of events. So that's why this is a very emerging area, and he have a lots of experience because he worked in NASA for a long period, was director in that lab, and apart from NASA, in IFIP also is highly, I mean, associated as a IFIP president. So that's why I think this gives a good purview to all the audience. So it will be helpful for all of them. Thank you.
Thanks, Nilanjan. Thank you.
So I now request our CSI group to hand over the certificate to Professor Hinche.
Thank you very much.
Okay.
Thank you.
So we have heard an excellent lecture by Professor Hinche, as expected. He has delivered his lectures so many times to us. So I thank him, and instead of clapping, I now clap on my own.
Thank you very much. Thank you. Appreciate it.
Okay. Well, back to the CSI.
Thank you, sir. With this, we come to we will be taking a short tea break from till 4:15. From 4:15 onwards, two technical sessions, technical session 5 and 6 will be starting. Technical session 5 will be starting in link 1, whereas technical session 6 will be starting in link 2. So I request all the participants to join accordingly. Please join ahead of time so that we can begin the session exactly at 4:15. The session chairs for session 5 is Professor Paramartha Dotto from Vishwabharati University, Mr. Rishabh Bakul from TCS Innovation Lab, Professor Ashish Kumar Mukhopadhyay Margdarshak AICT, and session 6 session chairs are Mr. Sumit Kumar Sinha, Head of Projects, Ericsson Global Services, Kolkata; Dr. Anindita Roy Chaudhary, Sarojini Naidu College of Women's, Kolkata. So after this session, there'll be another 2 technical sessions, 7 and 8, which will commence from 6 p.m. onwards. Again, technical session 7 will be in link 1. Technical session 8 will be in link 2. So we can take a short break and let us rejoin at 4:15. The session will end for now. We will reactivate the session around 4:05 p.m. IST. Thank you, everyone.
Bye, Mike. Thanks, everyone. Bye.